we're going to start off just by reviewing what we did last class. We were talking about the test for increasing and decreasing, and you guys should have done this on your WebWorks. And then we were also talking about the first derivative test. Who remembers what the first derivative test tells us? Someone, anyone? The first derivative test, what piece of information does it give us? No, it doesn't give us critical points. We use those critical points for something, but it's not giving us the critical points.
Is it the local max and local min?
Yes, good job, Kiana. It's the local max and the local min. And that's actually really important because today we're going to learn two more tests. And the names of the tests, it's going to be important that you are capable of saying, oh, this told me to use the first derivative test, therefore I find the local max and min. Because oftentimes these questions just say, apply the second derivative test. And you have to know what that means. So this is for local max and min, and the test for increasing and decreasing is the thing that tells me about increasing and decreasing. So we're just going to remind ourselves briefly about the steps that we follow to apply the first derivative test so that we can kind of have them in a clear way. Or rather, we'll call this guidelines for the first derivative test. Oh my gosh, this is going to be a bad day. I cannot spell. First derivative test. Oh my gosh. I literally forgot a letter in every single one of the words that I tried to write. Okay, so guidelines for the first derivative test. We saw last class that the first thing that we do is we actually apply the test for increasing, decreasing. Then we said that it is important every single time to make sure that your critical values are not discontinuities. Make sure that you don't have a vertical asymptote there or a removable discontinuity. So we're going to be sure to label any discontinuities from f prime if x does not exist. And we do that by asking the question, does the original function exist at this point? And then we apply the test. Remembering that discontinuities cannot be maxes or mins. So these are our guidelines for applying the test. We're going to do one example to kind of remind ourselves of everything that we did last class and kind of have these guidelines in mind while we're doing that. And then we're going to learn a new test. Okay, so let me know in the chat when you guys are ready to move on. Are you guys spelling something? Top? Okay, all right, let's do this thing. So find the intervals of increase and decrease and any local extrema of f of x is equal to 3 times the cubed root of x squared plus 1. X squared minus 1, my bad. So our first step is when we're applying the test for increasing and decreasing is to find the critical values. And to find critical values, we know that we need to find the derivative. So f of x is equal to 3. I'm going to rewrite this x squared minus 1. What power does a cubed root give me? 1/3. You got it. So this is to the power of 1/3. So then when I take my derivative, f prime of x, I bring that 1/3 down. It gets multiplied by 3. So there is no, so 3 times 1/3 is just 1. So then this is x squared minus 1, x squared minus 1 to the negative 2/3, and I'm applying a chain rule here, so I pull out a 2x. And now remember, for finding critical values, we want our derivative simplified. And this is almost as simplified as it gets, but remember we've said that in our simplified form of the derivative, we don't want any negative exponents left over. So that means I'm going to bring this down and have 2x over x squared minus 1 to the 2/3. So we're just going to make a note here to kind of remind ourselves, since it's a new day, to find critical values, we want the simplified derivative, and therefore we don't want any negative exponents left. Oops. Okay, so that is our first step of applying the test for increasing and decreasing. So our second step is to actually use that derivative now to find the critical values. So remember, our first step is derivative simplified. Our second step is critical values. And who remembers where critical values occur? You got it. When f prime equals to 0 and f prime does not exist. So that's what we're going to do now. We're going to set f prime equal to 0. And remember that when we have a fraction, this is like setting the numerator equal to 0, which means that I'm just looking at 2x equals 0. And so I only get one value there, 2x. And then I'm going to see where f prime does not exist. And again, when we have a fraction, this is where the denominator equals to 0. So I x squared minus 1 to the 2/3 equals to 0. The power doesn't matter, so I end up with x squared minus 1 equals 0, which gives me which x values?
It's +1 and -1.
+1 and -1. So Yes and no, David. So if we had just x minus 1, if the denominator wasn't squared, then yes, potentially we could have like the square root of a negative number on the bottom. So like if I ended up with the square root of x minus 1. But the fact is that what we have here, this power, is to the power of 2/3. So it's a cubed root and not a square root. And so the cubed root of a negative number does exist. So the problem would be if we had a square root and not a cubed root. Does that make sense? And does that answer your question? Okay, so this gives me x is equal, thank you, Alex, to positive and negative 1. Now, next, I'm going to go up here to these guidelines that we gave ourselves this morning for the first derivative test. Actually, I'm going to put them in a little cloud to separate them. It says, be sure to label any discontinuities from f prime of x by checking if f of c exists. So when f prime of x does not exist at these two values, we remember we need to check if f exists at 1 and negative 1. So here we're going to have this like extra thing, does f exist? So first I'm looking at f of 1. What does f of 1 equal? I get 3 times the cubed root of 1 minus 1. What's that? You got it. It's 0. Does 0 exist? A lot of you had a few problems with this semester. Yes, 0 exists. 0 exists, so that's not a discontinuity. Not a discontinuity. Wow. Continuity. Okay, so then we're going to do the same thing with f of negative 1. And I'm going to get 3, the cubed root of negative 1 squared minus 1, which also equals to 0, which also exists. Okay, so now we ended up, f of 0 doesn't matter. And because we said the only values that we need to check are the ones where f prime doesn't exist. Because if f prime exists, that means the derivative exists. And if the derivative exists, that means the function exists. All right? So what we've said is that a function can not be differentiable but not continuous. So if the function, in other words, if it's differentiable, then there is function. Does that make sense? Okay, so we only have to check the does not exist side, and that's why up here in our guidelines even, we're saying be sure to label any discontinuities from f prime does not exist, because that's really the only ones we actually need to check. Okay, so this brings us to our third step. We have 3 critical values here. And those 3 critical values are negative 1, 0, and 1. And in our third step, that's when we set up our variation table. So we're going to have interval, and I'm just going to write I for interval, and we're going up, we're separating at all of our critical values. And then TV is for test value, where we pick our number of our choice on each of these intervals. So I'm going to pick negative 2, negative 1/2, positive 1/2, and 2. Then we want to know about the sign of f prime, and we want to know what that tells us about f. And to figure that out, we plug these values in to the derivative. So I'm saying f prime of negative 2 is 2 times negative 2 over negative 2 squared minus 1 to the 2 over 3, which gives me negative over positive, which is negative. Now, a thing that might be helpful to think about here is that this 2 on the top here is saying that the denominator is being squared. And if something is being squared, is it ever negative? No. So that 2 means the denominator is always positive. What's up, Kareem?
What's the TV in the second column? I didn't get it.
Test value.
Oh, right.
So we're
Oh, so
picking
you
a
just take
value on
random.
each interval.
So you just take a random value and then
Exactly. So
inside
I'm
the
just
interval.
picking a random value between negative infinity and negative 1. So like, for example, could I have picked negative 84 if I wanted to? What do you guys think?
Yes.
Yes. So typically we want to pick values that are just easy to plug in, but you can really pick anything as long as it's on that interval. So this means denominator is always positive. Okay, so then, So then I'm doing the same thing for negative 1/2. So I'm like f prime of negative 1/2, and that's going to be a negative on top and a positive on the bottom. So that's negative, then f prime of 1/2. I know the bottom is always positive, so I really don't have to think about that. 2 times positive 1/2 is positive. And then f prime of 2 is also positive. Did I get any values that were discontinuities? You got it, okay. No, there were no discontinuities, so there's nothing I have to label down here. So in terms of like these guidelines up here, there's nothing to label for step 2. So I'm gonna apply the first derivative test. I'm gonna finish applying the first derivative test. Applying the test for increasing and decreasing, and then I'll use that to make conclusions about maxima and minima. So negative means that it's decreasing, and positive means that it's increasing. Now it was continuous at all of those places. So to apply the first derivative test, so that's what we're doing here. Now apply first derivative test. And here at step 4, I applied the test for increasing and decreasing. So what would the first derivative test tell me about maxima and minima? Do I have any?
You have a local minimum.
You got it. I have one local min right here at x equals to 0, because we can see that it's going down and then going up. Now these are places where it is continuous but not differentiable. So what could those be? What's a possibility for what those could be?
Curves.
Could be a cusp or corner.
It could be a cusp or a corner. What's the other possibility?
A vertical tangent line.
Or a vertical tangent line. You guys got it. So this is not enough information to tell me which, because like I could have a cusp or a corner that looks something like that, right? Where it's decreasing and then decreasing. But it could also be a vertical tangent line where it kind of does something, maybe it does like that. It turns out it's a vertical tangent line, but you guys don't need to be able to tell that from this right now. So we're going to make our conclusion here, which is that this is decreasing on negative infinity, negative 1, union, negative 1, 0, and it is increasing on 0, 1, union, 1, infinity. So that's my final answer about that part. Then I have a local min, at x is equal to 0, but remember we need to plug that value into the original function to get the y value. So that is 3 times the cubed root of 0 squared minus 1. And the cubed root of -1 exists. It's just -1. So this is -3, and my local min is at 0, -3. And that's my final answer there. There are no local max. We don't know this is global min because it's decreasing after the other decreasing, so it has to be smaller. Exactly, we don't know that it's a global min at all. It turns out that it actually is a global min. Oh, wait, hang on. So we do know that this is a global min, actually. You don't have to know that right now. But yes, exactly. We know that it's the lowest value because it's decreasing, and then from there, it's increasing forever. So there's no possible way that we could get lower than it. I'm actually going to draw a graph of this thing. So if that didn't make sense to you, you can kind of see what I was just saying there. This looks a little bit like this. So I know that there's a local min at 0, -3. So I'm going to plot that local min there. I know that it's decreasing on the left side and increasing on the right side, but I also have these other two values that I'm just going to plot that I found up here. 1 and -1 are both 0. And these are also 2 points that I have, and the only thing that I know about those 2 points is that it's not differentiable there. And it turns out this looks like this. It turns out that those 2 places are actually vertical tangent lines. And then that's my local min, which we can see from the graph is also a global min. And by the end of next week, you're going to be able to draw this graph all on your own. Are you excited? Yes. Okay. Are there any questions about this problem that we just did? Is that yes, that you have a question, or yes, that you're excited? So think about what a cubed root means. It says, what do you have to multiply by itself 3 times to get -1? Well, -1 times -1 times -1 is -1, right? So we're saying it's -1 because if I multiply that by itself 3 times, I get the result. Okay, so that said, we can see from this graph that that local min is also a global min. And last class we saw that what global min and global max are when it's lower than anywhere or higher than anywhere. And today we're going to actually, the next thing we're going to look at today is really going to have us thinking about that. It's called the extreme value theorem. And the extreme value theorem is a theorem that tells us how to find global min and max on closed intervals. Hang on 2 seconds, guys. Sorry about that. Okay, so the extreme value theorem, as I was saying, it's a theorem that gives me information about how to find global min or max on closed intervals. So if we're just looking at parts of a graph. So before I actually state the extreme value theorem, I want us to look at some graphs really quickly.
So would a closed interval be like an interval that doesn't contain negative infinity or positive infinity?
Yes, exactly. And so when we look at a graph, what that looks like is it's saying like, I have a clear point and a clear point that tells me this is where it is. It doesn't go on forever in any direction.
Okay.
Okay, so like if we look at this graph, this is a function on a closed interval because, as Alex just said, there's no infinity or negative infinity. It's not going on forever to the left or going on forever to the right. So that particular, closed interval would be if I call this value A and I call this value B, then my closed interval here is the interval AB. And if we think about how we defined global min and global max, is there a clear global min on this function? Yeah, that global min is right here. It's lower than everywhere else. So this is my global min. When I look at this, it's smaller than any other part of the graph, so it's my global min. And what is the derivative there at that global min? You got it. The derivative is 0 because this is a horizontal tangent line. So maybe you guys are slowly starting to understand why we had so much focus on horizontal tangent lines earlier in the class. Now, does this have a global max? I want you to remember the definition, where the y value is higher than anywhere else on the whole thing. Where does that global max occur? At what x value? You got it, David. It occurs at B. So
B.
this right here. Say again, Alex? What was that, Alex?
Oh no, I just said B.
You got it. Good job. So exactly, it occurs right here. That is my global max. And the thing about this global max is it occurs at an endpoint. So here, this is an endpoint. I could also have something like this, where there are no critical values on that interval, but there's still a global min and a global max because there's a place that's higher. And you'll notice that in this case, the global min and global max occur at endpoints. I want to look at just one more graph. I'm going to turn off my video for a minute because my internet connection is unstable and I'm worried that things are going to happen. Okay, so does this third graph have a global min and a global max? I'm going to label this again. We'll call this A, we'll call this B, and I'm going to call this in the middle C for my critical value. At what x value does the max occur?
C.
At C. So that's my global max. And what's the derivative there?
Non-differentiable.
Exactly. Good job, Luca. That's a corner. There is no derivative here. So at this place, f prime does not exist. Is that a critical value? Yes, because critical values are where f prime doesn't exist and where f prime equals to 0. Then it turns out that there are two global mins. and those global mins occur at endpoints. So what the extreme value theorem tells me is that if I have a function that's continuous on a closed interval, then it's gonna have a global max and a global min. And maybe that global max and global min are endpoints, but maybe they're also at critical values. So if we actually write this theorem out, the extreme value theorem. It says if f is continuous on a closed interval a, b, then f of x will have both an absolute, or we've been calling them global, max and min on the interval. More than that, this max and min can occur at critical values or at endpoints. And this is the extreme value theorem. So with all of our tests so far, we have guidelines for applying those tests. So we have the theorem and then we have the guidelines. So we're going to also write down some guidelines for applying the extreme value theorem. Which from now on, I'm going to be referring to as EVT. I.e. for finding global extrema on a closed interval. So the first thing that we're going to say is let f be continuous on that interval, which means that we're going to have a step 0, which is check that f is continuous. In other words, check that there are no values that cause division by 0 or that cause a negative under a square root. And then our real first step is to find the critical values that occur on the interval. And then we know that our global maxima and our global minima are when the y value is higher than any other value or lower than any other value. So what we're going to do is find the y values. So y values come from the original function. So we're going to evaluate f at each of these critical values. And then we're going to evaluate f at the endpoints. Because I know that those are the only places where my global max and global min can occur. Then the biggest y value is the absolute max. Biggest y value is my global max. And my smallest y value is my global min. And then these are my guidelines. So as soon as you guys have these down and are ready to do an example, let me know. All right, that's 1, 2, 3, 4, 5, 6, 7, 8. 8 of you done. Let me know in the chat when you are ready to move on. Okay, that's a lot of you. So let's look at 0. Our step 0 says, actually before I do this, let's read the question together. It says, find the global extrema of f of x equals to the function on this interval. The fact that it's telling you global extrema and it's giving you a closed interval, those are a clue that you need to be using the theorem and the guidelines that we just saw. So like these two things together are the things that tell you use the extreme value theorem. Right, so that means I'm not going to be making a table of values like with the first question we did today. I'm going to be applying these guidelines, which you'll notice don't have a table of values in them at all. I don't plug things into the derivative, I plug things into the original function with this. And being comfortable with that difference is going to be important. It's going to be the difference between doing well in the problem and getting 0 points because I can't even give you part marks because you made me a table of values when you were supposed to be using the extreme value theorem. So be careful. Use the things in the question to determine which method we should be using. So that closed interval and the word global or absolute here are an important part of this question. So then we're looking at step 0. Is there any possible division by 0 or negatives under a square root here? Well, there's no fraction, so there's clearly no division by 0. And there's no square root, so there's also no negative under a square root. We could even state the domain of this function. The domain of this function is R. There are no problems. So R means all real numbers, which we could also write as negative infinity to infinity. Now our next step is actual 1, to find the critical values that occur on the interval. So I'm taking my f of x is equal to e to the x squared times x squared minus 5, and I want to do the derivative of that. What rule do I need to do the derivative of this? You got it. I'm doing a product rule here. So f prime of x is equal to e to the x squared prime times x squared minus 5 plus e to the x squared times x squared minus 5 prime. What rule do I need to do the derivative of e to the x squared? You got it, Kenna. That's going to be a chain rule. So here I'm going to have e to the x squared times 2x times x squared minus 5 plus e to the x squared times 2x. And now we need to simplify. What is my greatest common factor? Wait for a couple
2x.
minutes.
2x times e to the power of x squared.
You got it. Exactly. So I've got the x, e to the x squared on both sides. I've got the 2 on both sides. I've got the x on both sides. So that's my greatest common factor, which I'm now going to factor out. So I'll have 2x e to the x squared. What's left in the first is x squared minus 5 plus what's left in the second? One. Be careful about that. A lot of people have this tendency to say, oh, I took everything away, there's nothing. That nothing is a 1, it's not a 0. So be careful about that. So then this is equal to 2x e to the x squared times x squared minus 4. Side question. This is a great simplified form for finding critical values, for finding horizontal tangent lines. Is this the good form for finding the second derivative, if I wanted to find a higher derivative?
No,
No.
because you have a double power rule. Product rule, sorry.
Product rule. I've got a double, yeah, exactly. I've got like 3 things multiplied together. So what could I do? What would be a better form? A better form if I needed the second derivative. What could I do if I wanted to find the second derivative? Tell me in the chat. What do you guys think? To help you guys along, remember we've said less product rule, less quotient rule, good. More power rule, good. So we're trying to like get rid of product rules and have more power rules. So what could I do to make that happen? Anyone? This doesn't bode well for you guys. Remember, we've said that especially in the case when you have an e, you want to separate the e part from the polynomial part. So this would be 2x cubed minus 8x. In other words, I would distribute that 2x cubed, that 2x back inside. And now I just have one product rule, and I turned what was a product rule into more power rules. Does that make sense? Are there any questions about that? Okay, so now we're still in step one. Remember, our step one here is to find the critical values that occur on the interval. So now I'm saying f prime is equal to 0. So in this case, this is 2x e to the x squared times x squared minus 4 is equal to 0. And I'm taking each one of those things and setting them equal to 0 separately. So I get x is equal to 0. What about e to the x squared equals 0? Does that ever happen? And if so, where? E to the 0 is 1. E to the x never equals 0. It just can't happen. So down here, we're going to write never. And if that's not something you were comfortable with, you should have a big star because it's something you need to become comfortable with. E to the x, e to any function will never equal to 0. So e to the g of x never equals 0. Know that. And then I'm doing x squared minus 4 equals 0. When does that happen? Plus or minus 2. Oh, yeah, you got it. So I got 3 critical values, but I only care about the ones that are on my interval between -1 and 3. How many are on my interval? So I have 3 critical values, which are -2, 0, 2, blank critical values on interval, which is -1 to 3.
-2 isn't involved.
-2 isn't involved, so I've only got 2 on the interval. That -2 is not important. So I'm only looking here at 0 and 2. Now I have a tendency to combine steps 2 and 3 here. I want to evaluate f at my critical values and my endpoints. So I'm going to do this as step 2 and 3 together. And I'm going to be looking at my endpoints. So I'm going to be doing f of -1, my critical values, f of 0, f of 2, and my other endpoint, f of 3. So this is the critical values and the endpoints. Kenna, why would that be a critical value? If e to the x squared is equal to 1, then this doesn't equal to 0. And also, I mean, we could go up here and no, we also have to look at where f prime does not exist. But because we don't have any like division by 0 or anything, this just never happens. So like the only places are when it equals to 0 or when it doesn't exist. But like, does that make sense? Okay, so now I'm going to plug these in to my original function, which we'll remind ourselves is f of x is equal to e to the x squared times x squared minus 5. So here I'm getting e to the negative 1 squared times negative 1 squared minus 5. And this gives me negative 4e. And then I do e to the 0 times 0 squared minus 5. And that just gives me negative 5. Then e to the 2 squared times 2 squared minus 5 just gives me negative e to the 4th. E to the 3 squared times 3 squared minus 5 gives me 4e to the 9th. And now my step 4 is to find the biggest and the smallest of these values. So step 4 said, biggest y value is the global max, smallest y value is the global min. Because these are in terms of e, it's a little bit hard to compare them. So this is the time where I can use approximately equal to and actually think about decimals. So this is like negative 10.87. That just equals to negative 5. This is negative 54.598, and this is approximately 32,412.33. Which one of these y values is biggest? F of 3, you got it. So that's my biggest. What's my smallest?
F of 2.
F of 2, this is my smallest. And so that means I can conclude that that is the absolute min and this is the absolute max. So I'm just looking at the biggest and smallest of the y values. Which means my conclusion here would be that there is an absolute or global, you can use whichever you want, min at 2 negative e to the 4th. And I know you guys have a lot of trouble with this. You keep losing points on your group work for it. Decimals in your final answer are not okay. So if you go and you write 2 negative 54.598, you will lose points. I need to see that negative e to the 4th, which is why that's how I solved for them to begin with. Then my absolute or global max is at 3, not negative 54.598, not 32,412.33, but 4e to the 9th. And this is my final answer.
How do you know that like they equal that, or they're like approximately that?
I plugged them into my calculator.
Oh. Okay.
Yeah, like I definitely could not look at 4e to the 9th and do that in my head, so. Do you know how to plug that into your calculator?
Probably find the button.
The E button is the one that's under the lawn button. So if you press like second E, then it should give you a chance to like give an E value. So it's like right there under
There's the one
button.
Yeah, it's the one that says e to the x.
Exactly that one. So like if you press second and then that button, is my calculator dead? Oh no. Second and then that button, then you can do like e to the 9th and then multiply it by 4 and there you should get the value.
Yeah. Okay.
Cool. Okay. Any other questions? right, then let's do a next question from start to finish. Find the global extrema. So again, we have the word global, which could also be absolute. And we have this closed interval right here. So that tells us to use the extreme value theorem. And our step 0 is to check for any division by 0 or negatives under a square root. Am I going to have either of those in this problem?
You could have a negative square root. Never mind, it's cubed root.
Yes, good job. Never mind, because that's not a square root, it's a cubed root. So there is no division by 0. No negatives under a square root. This is a cubed root. And we saw in a previous problem, in the first problem we did today, that we can have the cubed root of a negative number. That's okay. So here the domain is just all real numbers or negative infinity to infinity, however you want to write it. So now we want to find our critical values. So I'm just going to rewrite f of x is x squared times x plus 1 to the 1/3. What rule do I need to do this? You got it. This is a product rule. That's my f, that's my g. So my f prime of x is the derivative of the first times the second plus the first times the derivative of the second. So I bring the 1/3 down, I subtract 1 to get negative 2/3, and then I multiply by the derivative of the inside, which is just 1. And now we want to simplify, so we need to simplify, so we're looking for the greatest common factor. What is the GCF in this case? So what is my GCF here, guys? That's almost part of it, not quite. Okay, so remember, we're going to go through and look piece by piece. Over here, I have a 2 on the left side. Do I have a 2 on the right side?
No.
No. Okay, so don't keep it. I have an x on the left side. Do I have an x on the right side?
Yep.
Which has the lower power, x or x squared?
X.
X, so I take my x. Then I move on. I have x plus 1s on the left side. Do I also have x plus 1s on the right side?
Yep.
Which has the lower power, 1/3 or negative 2/3?
Negative 2/3.
So that's what I take out, the x plus 1 to the negative 2/3. Good. So now I'm going to factor that out. So I'm going to have x times x plus 1 to the negative 2/3. And then I want to say, what did I not take away? Did I take the 2 away? No, that 2 is not part of the greatest common factor. Did I take all of the x plus 1s away? How many x plus 1s should be left here? You guys remember how to do this? Remember, we said I have 1/3 x plus 1s, and I took away negative 2/3. What does 1 minus negative 2/3 equal?
1.
1. So that means my new power here is just 1. Plus, in the same way, I'm doing exactly the same thing with the x squared here. I have 2. I took 1 of them away. How many do I have left? If I had 2 and I took 1 away, I have 1 left. And so I'm actually literally just doing the same thing. I'm like, here I had 2 and I took away 1. So I have 1 left. I did not bring that 1/3 with me, but I did bring all of the x plus 1s with me. So I close my parentheses. So guys, this did not show up on your midterms. So you can bet that this type of thing, dealing with that negative exponent, will probably show up on your final, dealing with those negative exponents or those fractional exponents. So please take the time to make sure that you understand this. Okay, so now I'm not done. Remember, now I need to expand and combine like terms. So here I'm going to have x times x plus 1 to the negative 2/3 times 2x plus 2 plus 1/3 x equals x times x plus 1 to the negative 2/3, 2x plus 1/3 x, that's 7/3 x plus 2. Okay, so is this my simplified form, or do I still have something left I need to do? Based on, for example, something we talked about earlier today.
Negative exponents.
Negative exponents. We want to make sure that we don't have any negative exponents. So now we deal with the negative exponent. Okay, so my final simplified f prime is x times 7/3 x plus 2 over x plus 1 to the 2/3. And this is my simplified f prime. Which now I'm going to use to find my critical values. So I'm setting f prime equal to 0. That's my numerator equals to 0. So here I get x is equal to 0. And 7/3 x plus 2 is equal to 0. Which I need to solve. So I can bring that 2 over to the other side to get 7/3 x is equal to negative 2. What can I do now to solve for x?
Times 3 on both sides.
I can start by multiplying by 3 on both sides. but I can actually just flip the fraction. So I could even multiply by 3/7 on both sides to get that x is equal to -6/7. So right now I have x is equal to 0, x is equal to -6/7, and then I want f prime does not exist, which is like setting the denominator equal to 0. So I set x plus 1 equals to 0, and I get x is equal to -1. Are any of these values, remember my interval here was -1 to 4. Are any of these values not on my interval? They all count. This is on the interval. This is on the interval. And this is an endpoint, which means I'm gonna have to plug it in anyway. So we are thinking about that -1. So this now brings me to my step 2, which is to evaluate f at the critical values. Oh, am I lagging really bad for all of you? I think I'm lagging for myself too, actually. Uh-oh. Give me a sec. I'm gonna turn my video off again and we'll just see if that helps. Do you guys hear me now? Is that better a little bit? Alex is nodding his head. Okay, I'm gonna keep going. If I start lagging again, let me know, okay? Okay, so we're moving on to our step 2, and remember I said that I like to combine steps 2 and 3 so that I'm plugging in my values at the same time. So here I'm plugging in f of -1, f of -6/7, f of 0, and f of 4. And remember that our original function was x squared times the cubed root of x plus 1, if I'm not mistaken. Yeah, okay. So our original function was x squared times the cubed root of x plus 1. And I plug each of these things in. So I get, oops, -1 squared times the cubed root of -1 plus 1, which just gives me 0. Then -6/7 squared times the cubed root of -6/7 plus 1, which gives me 36/49 times the cubed root of 1/7. Am I still lagging for you guys? Because I'm still lagging for myself, actually. It's taking a long time for it to get from where I write to the screen. I think that means I must be.